Good morning, sixth grade. Yesterday we started learning about Newton's first law, and his first law of inertia is what he calls it. Basically says that an object in motion will stay in motion, or an object at rest will stay at rest unless acted upon by an unbalanced force. And it's usually a force that gets something to move or to not move. So we gave yesterday the example of the guy on the motorcycle as he's riding and he hits the wall, but he keeps flying. He wanted to keep moving even though the bike had stopped, and the unbalanced force that got him to stop were what two things? That's right, gravity and friction. And then we talked about like having to overcome those forces, like pushing someone on a swing. If I have someone who's super heavy, it takes a lot of effort to get it to overcome that inertia to get that person to start moving. But once they start going in motion, it doesn't take much effort to get them going because now they're already in motion. The resistance to motion would be if I walked in front of someone as they were swinging and just stood there and they hit me as I tried to stop them. That would be really difficult to get them to not move. So I've recorded myself giving some examples of inertia, and I'm going to walk you through that. On the webpage, there's instructions for your assignment today. Please follow all of them all of them. There's going to be about 3 or 4 steps that you're going to have to do. Plus a bonus that you have the option of doing as well. So enjoy. All right, we're going to start with this example called cup and nickel. And I have a cup, I have the card, and then I have a nickel as well. And I'm going to set the card on there. And before I do anything, whoa, let's back it up a little. Before I do anything, what object is at rest? The nickel's at rest, that's right. And it's going to stay at rest until I put it into motion. Well, let's see what happens if I hit the card instead of the nickel itself. Let's do it one more time. I have the nickel, I have the card, and if I flick the card, the nickel just drops. Now, it drops because that nickel just wants to stay at rest, right? Now, how could I make this different? What resistance to inertia could have changed the whole outcome of this little experiment right here? What if I had a piece of carpet that the nickel had to sit on and I tried to flick that piece of carpet? What resistance to inertia or agent against inertia would cause some problems? Yeah, friction. The nickel would probably slide. There's like no friction on this card, therefore it's able to slide right off. All right, next I have a 2-cup tower. We're going to do a 2-cup and a 3-cup tower. Let's see what happens. So I have the cup stacked and I have a piece of paper plate. And the cup wants to resist that urge to be put in motion. So instead of it flying off to the side, like you would think, what is happening? Three cups. That's right. Inertia is just causing the cups to fall straight down because there's no friction pulling the cups to the side. They're example of inertia, the resistance to go into motion is they simply just fall straight down. All right, now we're just getting kind of crazy. We're going to try with 4 cups now. Let's see if this works. So all these cups want to resist motion, so they just want to fall straight down. Let's see if we can get that to work. Yeah, I'm doing like my own Dude Perfect. Yeah, all right. Let's go. Right? Isn't that what they normally say? One more time. Let's see this resistance. There we go. Inertia. So an object at rest will stay at rest. Are they at rest? They absolutely are. They will stay at rest Now what happens if I came over and just kind of like hit the stack? Of course, they're all gonna fall. All right, let's look at one more example. All right, let's get super crazy. I have an egg, I have a paper plate, and I have a little tower here. The egg is the example of inertia. It wants to stay at rest. Even if I move what's under it, it's going to drop straight down, which means it's still resisting that urge to move. It simply just dropped straight down because, well, it had to. Gravity brought it down to the ground, right? Isn't that one super cool? You should try that at home, guys. But make sure you don't do it where you can get egg everywhere if you mess up. Let's go! I lied. Here's the last one. You all have tried this before, and this is an easy one for you guys to try. I know for sure you have coins lying around your house, but I have this nickel on my elbow here, and I want to be able to catch this nickel. The resistance to a change in motion is the fact that this nickel is just going to do what? It's going to fall down, which gives me the opportunity to catch it, correct? What would be pretty awesome is if you guys could try this, but stack like 2 or 3 nickels or pennies. This nickel is not flying to the right, to the left, to the, back to the front, whatever. It's simply falling straight down because it's resisting the urge to go in motion. The only thing that's acting on it is gravity pulling it straight down until I spectacularly caught it. Your first assignment today, and all these assignments you are going to either type it up in an email or write it on a piece of paper, or you can print off the paper that I have that you can just copy your answers down and email it to me. But this is the first one. You're going to read these 4 questions and you're going to answer them to the best of your ability. The first one is, which is an example of the law of inertia? Second one is, what is inertia? Third one is, what is an example, which of these is an example of the law of inertia? And this one is, what is another name for Newton's first law? Next question you're going to answer is, describe the law of inertia and how it would relate to passengers on a train that is slowing down suddenly. So how does the law of inertia relate to people sitting on a train? They don't have seatbelts on, and the train stops all of a sudden. What happens to those people? So how does the law of inertia relate to those passengers? Last but not least, you are going to take this, you're going to go to this link right here. I will put a link button underneath this video to go to this video. And you're going to click on law of inertia, and you're going to play through that simulation. It's going to ask you to click some buttons to follow along with it. Now, sometimes, depending on the web browser you use, it sounds like Isaac Newton is having a stroke, or I don't know, something. His voice, it's just a jumble of words. I don't even know if they're words, but it has stuff written there so you can read along. And then you're going to answer these 3 questions based on that simulation. The first question, what kind of force is required to actually move the apple? The second one is, why does the worm continue to move even after the apple has stopped? And 3, what kind of force is required to stop the motion of the worm? I know you're like, a worm in an apple, what is this? Don't worry, you'll see when you watch this video. Again, I hope you enjoyed my Dude Perfect-esque experiments and object lessons for the law of inertia. Do your best to answer all those questions. Again, get all of those done and send them to me. That will be worth 100 points for this week. And if you want bonus, and I know some of you, Vanessa and Brianna, you're like dying to get this. Brandon, you guys, if you want a bonus, any bonus points for this, I want you to try any of those observations that I showed you, any of those examples, whether it was the nickel on the cup, the nickel on your elbow, the egg tower, the cup tower, any of those things. I want you to record yourself doing that, but showing a parent or a sibling and explaining why that is happening. If you do that, Chase, I know you will, make sure that you send that to me in your email as well, and you'll get bonus points. All right, guys, once again, I miss you guys. I love you guys, and I can't wait to see your answers.